Hello everyone, welcome to the video on Target GPAT 2022 series, and it includes all the multiple choice questions from the previous GPAT examination. In this video I have explained UV visible spectral concepts that are tested in GPAT examination. I have given the basic explanation which will cover all the concepts from UV visible spectroscopy. This is my YouTube channel. If you like the video, do subscribe and share. Let's get into the topic. Now, the UV visible region in electromagnetic spectrum of radiation is. Now understand the question. The question is about the UV visible region. Now 200 to 400 relates to UV region only. The question is about UV and visible. Now 400 to 800 related to visible spectra only. So the question is about the complete spectrum of UV and visible. It includes 200 to 800 nanometer. So the answer here is UV visible encompasses 200 to 800 nanometer. Don't be in a hurry. These kind of questions are a kind of trap. Don't fall into the trap. 200 to 400 is only of UV region. 400 to 800 is of only visible region. UV visible includes 200 to 800 nanometer. For all the practical purposes, 200 nanometers to 800 nanometers includes UV, ultraviolet and visible region. Moving to the next one. Now, the region of electromagnetic spectrum below 200 nanometers is known as. Now, let us understand this thing. See, we have ultraviolet region is there, visible region is there, infrared radiation is there, and then microwave radiation is there. See, arrangement of radiation in increasing order of wavelength is known as electromagnetic spectrum. Now, in this again, the regions which are closer to visible are known as near UV, whereas farther to this visible are known as far UV. What is the range of UV? We have seen from 200 to 400 is what UV region is. From 400 to 800 visible starts. So out of this 200 to 400, 300 to 400 is close to visible, hence it is known as near UV. Whereas the other one 200 to 300 is far from visible, so it is known as far UV. There is a region known as extreme UV that is less than 200. So in this side it goes to 100 to 200 nanometers. Now the question is the region of electromagnetic spectrum below 200. So below 200 region is known as vacuum region. Vacuum UV region. There is a reason for this name. The reason why it is called as vacuum UV region is, see, our atmosphere contains nitrogen and oxygen. 78% is nitrogen, 21% of atmospheric gas is oxygen. So both of these gases will absorb at this radiation. So if you want to conduct an experiment at this region, you need to flush out the atmospheric gases. That means you need to create vacuum. Hence, the region less than 200 nanometers is known as vacuum UV region. So the answer for this, the region below 200 nanometers is known as vacuum UV region. Whereas far UV is only from 200 to 300, whereas near UV is 300 to 400 region. Microwave region is far from this. See, after visible you get infrared and then you get microwave region. Now understand the names also. See, when you see the radiation names are given in a particular order. When you see this, look at this. Visible starts from violet, indigo, blue, green, yellow, orange and red. The radiation after this red is known as infrared. The red is taken from here. After this red it comes, hence it is known as infrared. Whereas the radiation less than this violet is known as ultraviolet. The violet is taken from here. So from this visible VIBGYR, after red you get infrared, before violet you get ultraviolet. This is how these are named. So now coming back to the question. So the answer for this question is below 200 nanometer region is known as vacuum UV region. Moving to the next one. Now which wavelength of ultraviolet light has maximum germicidal action? Now again we need to understand UV, A, B and C. See, these three regions are known as UV regions. Every region has got a particular wavelength. Now from 320 to 400 nanometers is known as UVA region, whereas from 280 to 320 nanometers is known as UVB region, whereas from 200 to 280 is known as UVC region. Now see, as the wavelength decreases, energy increases. So in this way, the energy is increased. So highest energy one is UVC. Now fortunately, this highly energetic UVC radiation will not get into the atmosphere because ozone layer will screens completely UVC radiation. So we don't get any of UVC because ozone is screening it. Whereas UVB is also energetic, only 5% of it reaches to Earth, and this is what this affects our epidermal layers, and this is responsible for cancer and sunburns. So the reason why people get sunburn and prolonged exposure of this UVB radiation is what causes cancer, and it also results in sunburns. Whereas UVA, 95% of the UV which reaches to the earth is UVA radiation, and this is responsible for photoaging or wrinkling. You know, too much exposure to sun causes wrinkling, which is also known as photoaging. It is because of UVA radiation. Now, among the three, UVA, B, C, highest energetic one is UVC, and this UVC has got germicidal activity. Germicidal. Side means to kill. Germ means germs. Germs will get killed because of this radiation. This is the reason why it is used in water purifiers. And this is also comes when welding kind of operations are carried out. So UVC will not reach us, but it has got germicidal action. Hence it is used to purify water. So the answer for this is UVC. We have already seen what is vacuum UV is. Anything less than 200 nanometer is what is known as vacuum UV. But answer for this question, maximum germicidal activity is there with UVC radiation. Please take a screenshot of this one, which is important. Every reason is important. Moving to the next one. Again, see the same thing. Which UV rays causes cancer? UV. Remember, all these questions are given in previous GPAT examination. All of them are basic concepts which are tested from UV visible spectra. And the cancer is because of UV. As we have seen, UVA causes photoaging or wrinkling. UVB, it affects epidermis and it may be responsible for cancer and sunburns. UVC, germicidal activity. Now energy absorbed in UV region produces changes in. Now again, this is a kind of tricky question. UV spectra is also known as electronic spectra. But understand the question. See, when a molecule is provided with energy, there may be changes in its rotation, and that is what is called as rotational spectra. Or the bonds may get vibrated. This is called as vibration. Or electronics may move from one energy to another energy. It is known as electronic spectra, electronic transitions. Now see, energy is quantized. That means to get rotations, microwave energy is enough. Whereas to get vibrations, infrared radiation is required. Whereas for electronic transition, ultraviolet radiation is required. But when you give ultraviolet radiation, it includes all the three: rotation, vibration, and electronic changes will occur. Electronic energy changes will occur. So the question is, energy absorbed in UV region produces rotational, vibrational, and electronic energy. So the option D is correct. It is not only electronic, it includes all the three. This is again a tricky question. Moving to the next one. Now the electronic transition not observed in UV is. Let us understand about this electronic transition. Now see, we have three different kinds of electrons are there. Sigma electrons, pi electrons, and n electrons. Sigma bond, a single bond is formed by sigma bond, and the electrons which participate in this bonding are known as sigma electrons. Whereas double bond, one bond is sigma, another one is pi bond, and these electrons are known as pi electrons. Whereas n electrons are non-bonded electrons which are present in heteroatoms like nitrogen and oxygen. They have got lone pair of electrons. They are known as n electrons. So when energy is provided, imagine, say this one is sigma electron. When energy is provided, the sigma electron may move from here to here. So this is called as sigma anti-bonding orbital. So you have bonding orbitals and anti-bonding orbitals. When you provide sufficient energy, the electron moves from bonding to anti-bonding orbital. This transition is known as pi to pi star. So this energy gap is very high. Usually it occurs at 100 to 200 nanometers. Practically, we don't use this kind of wavelength in UV spectra. The reason is you need vacuum, because air like nitrogen, oxygen absorbs it. So practically we don't see this kind of transition in UV. So the question is about this one. Electronic transition not observed in UV is sigma to sigma star. These are not observed in UV. What are the remaining? The other thing is pi bonds are there. Look at this. See, this is the energy gap. This is the energy gap. So these are pi electrons and pi bonding orbitals. So in this, pi electrons are there. When you provide sufficient energy, they will move on to anti-bonding pi orbitals. Now see, this energy gap is less, and see, UV radiation provides the energy required for this kind of transitions. Now after that you will have n electrons and non-bonding electrons. They can move from n to pi star also. So these are all what the transitions which occur, bonding to anti-bonding orbital. So most of the time in UV we see n to pi star transitions and pi to pi star transitions. So this is what is about UV visible spectroscopy. Now the electronic transition possible in Benzaldehyde is, now look at this, Benzaldehyde, benzene with an aldehyde group. So this is what is Benzaldehyde is. Now see, oxygen has got lone pair of electrons, that means n electrons are there. So there is always chance for n to pi star transition, and pi bond is there. So there is always chance for pi to pi star transition. So pi to pi star is also possible, n to pi star is also possible. P and R. So P and R, option C is the right answer. Moving to the next one. Now, increase in the extent of conjugation of a double bonded system results in. Now let us understand this. See, the major use of UV visible is conjugated system, to find out conjugated system. Conjugated system means the system which contains alternative double bonds. Like this, see, a single bond, double bond, single bond, double bond. This kind of system is known as conjugated system. Now, these kind of systems will absorb maximum at UV visible region. So the moment you increase this double bonded conjugation, higher wavelength will get absorbed. I'll give you one example. Take for the example ethylene. Now ethylene absorbs at 175 nanometers, whereas butadiene, see, conjugation, see, double bond, single bond, double bond. Now this one absorbs at 270 nanometers, whereas hexatriene, you increase one more thing, see, 1, 2, 3. So double bond, single bond, double bond, single bond, double bond. So hexatriene absorbs at 260 nanometer around. Now look at this, what is happening. The moment you increase conjugation, the absorption is going to higher wavelengths. So this is what is the question about. The extent of conjugation of double bond results in higher wavelength. For this, there is a specific name is there. Now let me explain it even in a subtle way. Now look at this. Now imagine the x-axis related to lambda or wavelength. This one is relates to intensity. Now let us understand this thing. Now if a particular group or something, the presence of that group causes absorption in increased wavelength, it is known as bathochromic shift. Bathochromic shift. Whereas a particular group, if it is causing absorption in lesser wavelength one, this is known as hypsochromic shift. Now what is the question about? The extent of conjugation of a double bond system results in double bond. If it is increased, just now we have seen in ethylene it is only 175, whereas butadiene it goes to 217, whereas hexatriene it goes to 250 or 260. So increase in wavelength means it is causing bathochromic shift. So the answer is bathochromic shift. Then what is hypsochromic shift? If a group is causing absorption in lesser wavelength, it is called as hypsochromic shift. Now hyperchromics relates to intensity. Intensity means if a group is causing absorption at higher intensity, it is known as hyperchromic shift. Whereas if a group is causing lower intensity, it is called as hypochromic shift. See, chroma means color. This is what you need to understand. So these four are important thing. One, wavelength one, if it is causing absorption at higher wavelength, it is bathochromic. Lower wavelength, it is hypsochromic. Whereas absorption intensity to higher intensity, hyper, lower intensity is hypo. This is it. Moving to the next one. Now, a moiety of a molecule responsible for selective absorption of radiation in specific region, especially UV and visible region, is called as chromophore. Now, you need to understand this word. You know, in pharmacology, we read about pharmacophore. Pharmacophore means a group or functional group, combination of functional group which are responsible for its mechanism of action. So, phore means a particular moiety. Pharmaco means its mechanism of action. Pharmacology is related to that particular group. When you say chromo means color. Phore means a particular group or functional group. So this functional group is causing color, and that is what is called as chromophore. Now, if that particular group or functional group is causing absorption at UV visible region, it results in colored compound. Hence it is known as chromophore. Chromo means color, phore means the group is causing absorption in UV visible region. That is the reason why it is getting color. So answer is this one, chromophore. Now, a dye is a substance which contains, now understand this one, the dye industries, the reason it is called as a dye is it will produce an intense color. To get that intense color, it needs to have chromophore as well as auxochrome. Just now we have seen chromophore is a group which is responsible for absorption in UV visible region. That means imagine something has got this kind of group. Conjugated bonds are responsible for absorption in UV visible region. Auxochrome means the groups which has got this lone pair of electrons. The lone pair of electrons will cause electron donation and increases the extent of conjugation, and that intensifies the absorption intensity. So it gives an intense color. So dyes should contain both of them, auxochrome as well as chromophore. So both the above is right one. Don't be in a hurry, not the chromophore, not the auxochrome. Both of them are required in a dye. So option C is the correct one. Going to the next one, Beer's law states that. Now let us understand what do you mean by this Beer's law. Now Beer's law in simply put, it is A equal to epsilon BC. Now A is nothing but absorbance. That means you take an organic solution, how far it is absorbing is based on, this is called as molar absorptivity. This molar absorptivity is very specific for a particular molecule. Every molecule has got different molar absorptivity. Now what is important is this one. C means concentration of the particular solvent. B is path length. Now if you read about UV visible, in UV visible sample is placed in a particular thing called as cuvette. So this cuvette, the width of this cuvette is known as path length. Usually it is 1 centimeter. So absorbance is depend upon concentration and path length. What does it indicate? It indicates if the number of absorbing species are more, the light absorption will increases. So if you increase this path length, what happens? More molecules will be there, so more absorption will be there. That is what is path length is doing here. Concentration, if you increase concentration, what happens? More amount of solvent solute molecules will be there, so absorption will be more. So absorbance is based on concentration and path length. That is what is about Beer's law. Now Beer's law states that, let us look at this. Absorbance of a solution is indirectly proportional to concentration. No, it is directly proportional to concentration. Absorbance of a solution is indirectly proportional to length. No, it is directly proportional to length. Absorbance of a solution is directly proportional to concentration and length of the cell. This is what is Beer's law is. So option C is correct. Transmittance of a solution is directly proportional. No, this is not correct. It is absorbance, not the transmittance. Transmittance is opposite to absorbance. So Beer's law, this absorbance is directly proportional to concentration as well as path length of the cell. Moving to the next one. Now reasons for deviation from Beer's law among the following are. Now see, Beer's law is strictly followed in specific conditions. Now the condition is monochromatic light. See, if you give polychromatic light, chroma means colored. See, a particular wavelength of light is passing through the sample, you will get exact result for Beer's law. If it is polychromatic, multiple wavelengths are there or intensity is more, you will not get a positive result for Beer's law. So monochromatic light is required. See, the question is about deviations is possible when there is a very high concentration of element. True. When the concentration is very high, it may not obey Beer's law. Now association of analyte, that means the analyte, if it is combining and forming a crystal kind of thing, it will not possible to get a positive Beer's law. Dissociation of analyte, if the chemical compound is dissociated, again this will not give a positive Beer's law. So deviation is possible when there is any change in chemical composition of analyte or when the concentration is too high. So deviation is possible in these conditions, Q, R and S. So option B is the right answer. Moving to the next one. Now, if organic compound does not absorb UV radiation, it means compound does not contain conjugated double bonds. See, the basic use of UV visible is to find out conjugated double bonds, alpha beta unsaturated compounds. So this is the basic use. If a compound is not absorbing UV, that indicates it does not contain conjugated double bonds. Now the effect of polar solvent on N to pi transition is, you need to understand this. Now when you see, now imagine lone pair of electrons are here and antibonding pi orbitals are here. This is what is there. Now lone pair of electrons, you know, on oxygen and nitrogen you have electrons like this. Now when you use a polar solvent, what happens is, because of these electrons, the polar solvent will stabilize these electrons. When there is a stability, it will go to lower energy one. So instead of here, see, by going upwards you are increasing energy. So when they are stabilized, instead of here they will come down here. So what happens, the energy gap between these two, instead of this one, it is increased to this one. So what happens, polar solvent increases the energy gap. When energy gap is increased, absorption occurs at high energy one. High energy one means low wavelength one. I have explained already, lower wavelength means it is hypsochromic shift. It is shifting to hypsochromic shift. Again, don't get confused. Understand this one. See, wavelength, when wavelength is increased, energy is decreased. Think about this one. We have cosmic rays are there, cosmic rays, X-rays are there, UV is there, visible is there, IR is there. Now, when you are moving from left to right, wavelength is increasing, but what is happening to energy? Energy is reducing. Right? Now look at this. When this transition needs higher energy, means it moves to left side, lower wavelength one or higher energy one. If it is moving to lower wavelength absorption, it is hypsochromic shift. So N to pi star transition in presence of polar solvent goes to hypsochromic shift. Now similar kind of question, the effect of polar solvent on pi to pi star. Now again understand this. These are pi electrons and these are pi star electrons. Now the polar solvent will stabilize more of this pi star electrons. So what happens, because it is stabilized, the energy comes down here. So what has happened, instead of this energy gap, the energy gap has reduced to this one. When energy gap is reduced, wavelength increases. Increased wavelength absorption is known as bathochromic shift. Again, just go through it again, you will get the concept clearly. Thank you for watching this video. If you like the video, do subscribe and share the video.